Hey folks! Okay, well, this time I want to talk about software testing. So we're going to talk about kind of the theory of it and a lot of the different aspects about software testing first, and then maybe in some of our later sessions we'll get into developing some tools to automate our software testing processes. So for testing in general, when we're going through gathering the requirements for the product, whatever it might be, from the user, we're really focused on the validation aspect of our requirements, trying to figure out if we're actually attempting to build the right thing, right? We want to make sure that we know what they want. We want to make sure that we document it correctly so that later on when we go to try and build the thing, we actually build the right thing. In the development side, once we start getting onto the coding, then we're trying to make sure that we're actually building the product correctly, that what we're building matches what the requirements say. So you've got that kind of two steps, the validation and verification, where you're trying to make sure you're trying to create the right thing, and then trying to make sure that what you created is actually the right thing. So we're going to break things down into kind of static versus dynamic. The static side is where you're not actually running the product. It's not actually in use. You're just looking at the product or analyzing the product, trying to figure out if it's going to do the right thing. So this is more the inspection and analysis side of things. So you can think of static verification as being the case where you're looking through the code, or where you've got a tool that looks through the code without running it and tries to identify possible problems. So we'll spend some time on code inspections later on, but that's the idea for the static side of things. For the dynamic side, this is where you're actually running it and trying to figure out if it's buggy or not. So testing the product in action, if you like. All right. So in terms of philosophy, a lot of people wind up starting their careers as testers, right? It's one way to get new employees familiar with the product and familiar with the behavior before you start throwing them into, sort of the nastiness of whatever the code might be. There's a bit of a reputation that testers get, shall we say, treated not so well by some other members of the community. Right? Just because the whole idea for testing is to go through and find any potential problems in the code. And a lot of developers aren't particularly pleased when people point out problems in their code. So just from a philosophical point of view, you do want to kind of get past that and keep things professional. Right? The idea is to make a better product by trying to detect any issues there might be in it now. The testers shouldn't be getting nasty with the developer if they do find a bug, and on the other hand, the developer shouldn't be getting nasty with the testers because they found a bug. So, in terms of general philosophy, when you're testing, you can find problems, but just because you didn't find a problem, it doesn't mean that the program's error-free. It just means that there might be something you haven't caught yet. Right? A good test is one that has a good chance of catching something that would have gone undetected otherwise. Right? So if you've got a bunch of tests and you add a new one that has a good chance of detecting things that weren't caught by your previous tests, that's a good test. Right? A test, having a whole slew of tests, having thousands of tests that all basically do the same thing isn't necessarily beneficial because they're all catching pretty much the same one bug. You want a variety of tests that are aimed at catching different kinds of issues. And again, a test is successful if it catches a problem. And again, finding the bugs during testing is a lot better than finding it when it's out in the field and the customer's already paid for it and is not very happy with you because you've given them a buggy product. Now, in relation to that, every test that you create should be able to test something new. It should have a specific reason for being there. Every test should be looking to prove that the product does or does not meet some requirement or some specification. Right? Every time you create a test, you're saying, okay, The specifications say this thing is supposed to work on values from 0 through 3012. So for sure I'm going to test 0 to make sure it works there, and 3012 to make sure it works there, right? Because those are the boundary points. Those need to work, and there's a good chance that if there's an error, it's around those boundaries. I'm going to test something at -1 and something at 3013, something that's just outside the bounds. And again, I have a reason for that test's existence. There's a high likelihood of errors right around the boundaries, so I want to test just inside and just outside the valid boundaries. So every time you create a test, you should have a reason you're creating that specific test. It's not just to fill in time and say, oh, well, I told the user I'd generate 100 tests, so I've got 99, let's just come up with some random value for the next one. Right? There should be a reason for every test you create. Now, one of the things that we can do, just like we looked at the idea of designing software that in a way that made it easier to debug, we should also be trying to design our software in a way that makes it testable. So if we have tightly cohesive code that's loosely coupled, if we've got a good use of abstraction, good modular design, we're going to be able to come up with test frameworks that work well and give us a good opportunity to ensure we've covered most of our code with good tests. And we'll get into the development of stubs and drivers and things for testing components and unit testing and module testing and that kind of thing as we go through this process. You want to make sure that any changes that you've made have been well controlled, well documented, well tested. Right? We're trying to make sure we're keeping this a good, cohesive, high quality process. And the next 2 points I want to get into are to do with how the nature of the code lets us test it well or prevents us from testing it well. So we've got these two ideas, and they're kind of borrowed from the hardware world, where a highly controllable value is something where we can generate a specific value. So let's say there's a variable somewhere in our program, or there's an output somewhere. If it's easy for us when running the program to force a specific value there, we call it highly controllable. Right? If I want to be able to create a case where a specific error is generated or where a specific output value is generated, if I can think of a set of input values or a control sequence that makes that happen, then we're saying it's highly controllable. So we want, ideally from a tester's point of view, we want a program that's highly controllable so that I can create all these situations that I want to test. And the flip side of that is the sort of highly observable, where it's easy for us to see what state a program is in. So in a sense, there's either directly or indirectly some way for me to observe what's happening to a variable or an object somewhere within the code. Right? Is it possible for me to at least infer what the value of something is from what happens with the output or from what happens with the way the program behaves? So highly observable means there's a good chance for us to be able to figure out what's happening internally based on what we're seeing externally. And things that aren't highly observable are cases where you've got some really convoluted set of actions taking place or computations taking place deep inside, and all you see at the end is one output value that's the result. Right? You have no real way of knowing what's going on inside that sequence of computation. If something goes wrong, we don't really know where. So highly observable, again, is desirable from a tester point of view, just because it means that we've got a good chance of saying, okay, well, if something goes wrong, I can trace it back to here. If I want to test something, I can do these things with the highly controllable side of it, and then observe what happened because it is highly observable. So those are kind of two aspects that you might want to have in the back of your mind. Again, you're not necessarily going to completely restructure your solution for the sake of testers, but if there are ways that you can make things more test amenable without damaging the rest of your design, then it might be a good idea. Now, one of the things that we'll look at is the idea of using tools to support control and observation. Right? We've seen that with the debuggers. The debuggers give us some additional ability to control what's going on, we can run the program, stop it at a certain point, and change the values of what's in there, right? That gives us some control. Or we can look at the values of what's in there. That gives us extra ability to observe. And so often tools are given to us or provided that, or we can create, that allow us to improve our ability to control and observe what's happening as the program runs. All right, in terms of the testing timeline, what traditionally happened for decades in project management was that we would go through, we would develop our program, and once we had it pretty well done, then we'd start thinking about how we were going to test it. It's a much better idea if you start thinking about testing early in the process. Right when you start working with your product, you say, okay, well, how am I going to test this? What am I going to test? When? So you can start developing your test cases and developing your test infrastructure as the rest of the project is going along. And it's not the case that you've got 1 month left till delivery and now it's time to start testing and we have to suddenly start building all this infrastructure to figure out how we're actually going to test the thing. So planning, development, and application should be a central part of the entire life of the project. We should be thinking about this right from day one. And you'll often hear talk about this sort of big V model of software development, where as you're going through the design and development stages, you're getting more and more specific. You've got this kind of top-down idea of requirements and then specifications and design and then coding. And then this sort of bottom-up, after that, this sort of bottom-up process of applying tests to individual units and then maybe to modules and then to subsystems and then to systems as a whole. And if I can steal Wikipedia's picky of this because it's a nice one, if we take a look, this is the idea of the big V. You're going through getting your initial idea of the product, you're doing your requirements, you're coming up with a design and architecture for it, you're coming up with a more detailed design, you're building it, and then you're testing the individual components, then you're testing the larger subsystems and systems, and finally you're doing your ultimate user acceptance tests for it. And the idea is that as time goes on, you're getting more detailed in your design, your implementation, and then your testing. But when we're going through this process, as soon as we know what it's supposed to do, we can start designing our tests to see if it does what it's supposed to. Right? If I know how the product is supposed to work, then I can start coming up with my tests saying, well, that means that if I do this, this, and this, I should get this as a result. So as soon as I know my requirements, my testing team can start developing user acceptance tests. As soon as I know the design of an individual module or class or subsystem, my team can start designing tests to see if that part works right. And so the idea is, as you're going through getting your more involved requirements, your more involved design, the test team is already building their test infrastructure to test the thing once it's ready. Right? When you're going through doing the detailed design for the interfaces for your individual components, your test team can be saying, okay, I'm going to put together the tests for each of those individual components. So your developers are working on getting the thing ready, while your testers are getting ready to test it. And as soon as your developer says, here, it's ready, we can start testing. And as soon as those pieces pass testing, then we can start testing on the subsystems or the systems. As soon as those are all ready, then we can go off and start testing, applying the final user acceptance tests. So you've got this idea of the whole thing as one integral structure where your teams are working in parallel. And because you came up with good documentation on what each of these things was supposed to do, your test team can rely on that and develop good tests. Now, again, it does mean that if you wind up just changing your requirements or changing your design, then your developers have to kind of backtrack a little bit and rework things for their design. It also means the testers have to be notified and have to rework things for their testing system a bit. But again, it means that we've got this integrated process, right? So that we're thinking about things right from day one. All right. Now, in that sort of an idea, there are different layers that people will talk about for testing. where you've got things like interface testing, where maybe you've got a bunch of methods for a class, and you haven't actually implemented them yet, but you can still test the framework, see that you've actually got the calls to a function correct, right? So you can actually make a correct call, passing the correct parameters. So all you're doing is testing the interfaces, just call and return. Does it work? All right, just getting a skeleton for your functions, for your methods up and running. Unit testing, where you have one individual method or one individual function, and you're just checking to see if that one thing does what it's supposed to do. Right? The rest of who knows what's going on with the rest of the product at the moment, but we're just checking to see if that one thing works. Or if you've got a bunch of units lumped together in a module, test to see if that one module works. And regardless of what the rest of the system is doing, just checking if that one thing works. And you get that same idea with subsystems. Does a particular subsystem work, in isolation from the rest of our overall product? Does a system work? Does it meet all of the acceptance tests for the client? And maybe once it does pass acceptance testing, we still go through that additional layer of throwing it out and letting people try it in real life, if you like, so that we can see if there are things that we hadn't thought of, things we hadn't anticipated that need to be addressed as well. So there are all sorts of different layers of testing that we'll take a look at. We'll also distinguish between sort of open box or closed box testing. The closed box testing is where you've got this kind of component and you can't look inside it. You just know from a user point of view, this is supposed to do blah. If I stick an integer in as a parameter, it's supposed to give me the square root of that, or if I give you a number going in, it should give me a square root of that going out. Or if I give it, an integer going in, then it should display a circle with that radius on the screen, right? You've got this idea of what's supposed to go in and what's supposed to happen, but you don't know how it's actually doing that. You don't know the implementation details inside the function or the method or the subsystem or whatever it might be. All you know is if I do this, it should do that. So the open box test is the idea that you can look inside. You can see how it's doing. You can see, oh, it's using an array for that, and it's using, these dimensions, and it's checking this constant as the maximum value. So you know how this thing's working. You can see what sorting algorithm it's using or what error testing it's performing. So the sets of tests that you'll devise are different for those two, right? For a closed box test, all you're interested in doing is seeing if it works from a user perspective. From the things that I'm expecting it to do, does it do those? Does it do the error checking that I'm expecting correctly? Does it do the output correctly? Does it seem to work according to what I want as a user of that, whatever that item happens to be, right? And user could mean, one of the developers. If it's a function that I'm writing and somebody else is going to be using it, then whoever's calling it is the user in that circumstance. Right, so it's going to be different based on whether I'm just using it or whether I'm actually looking inside it and saying, well, if I see that they're using this constant for the maximum possible integer or something like that, I'm going to try testing things around that value. Or if I see that they're using a particular sorting algorithm, then I'm going to throw data at it that I know is a worst case scenario for that sorting algorithm. Right, so with an open box test, because I know more about what's going on inside it, I can come up with nastier, more intricate tests for it. Now, I mentioned the idea of some static test tools, things that just look at your code, look at your program, and trying to figure out, if it's good or bad, more or less, quality checks if you like. Lots of compilers give you information about it, right? You can think about the different error testing flags that you can throw at your compiler to say, well, check this as well, and check that as well, and check this as well. And it might give you lots of warnings saying, oh, there's a possible problem here. So that is an example of static testing. And again, lots of software development tools can give you different levels of code checking at compile time to see if something looks incorrect. So code that can't be reached, variables that are used before they're set, array bounds that aren't tested, or that sort of thing. So all sorts of things that they can try and do for you. Some of them support things like path testing, where they will automatically generate a set of test cases that will force the program through every reachable line of code, right? Just to make sure that every line of code gets run at least once. And just, again, different things that can be done statically. Some tools will give data flow analysis, where they can tell you for each variable, what variables does that one depend on? So it goes through and looks at X and says, well, X depends on Y, which depends on Z, which depends on this other thing. Right? So they can go through and give you a static data flow analysis, where they look at your code and say, here are the things that this variable depends on. And that comes in useful in the debugging side of things, because it means that, if something's wrong with X and we know it depends, it was calculated from Y and Z, and that came from some other and some other and some other, then we can work our way back through and see what's going on. And from the point of view of observability and controllability as a tester, that gives us more information as well, right? That lets us know that, if I change the value of A and B and C and D depend on that, then by looking at B and C and D, I can start getting an idea of something that might be happening with A. Or if I see a problem in one variable, I've got an idea of where it might be coming from. All right, then we get into the actual running of tests, things where we're getting this thing running and we're trying to see if it works. And I'm going to describe these as functional and non-functional tests. So the functional tests are trying to see if the behavior is actually, if it does the things it's supposed to do. Does the program give the correct results? Does it give the correct output? For the non-functional tests, it's more a quality assessment, if you like. Does it meet the performance requirements associated with it? So if you said that, the program's supposed to compute the square root of blah to some degree of precision, then we might regard, does it get the correct result as a functional test? But if we want to specify it has to do it in such and such a time, it can't take more than so many microseconds to do this, or it can't use more than so much memory to do this, those would be regarded as non-functional requirements. The idea that we've got properties about the behavior that we want to assess as well. So you'll often see this kind of breakdown of things into functional or non-functional, and the non-functional are just looking at things like, does it respond quick enough? Does it use more memory than it should? Is it processing enough data quickly enough? Is it, and again, if we think back to our non-functional specifications discussions from earlier, does it meet the requirements for quality assessment as opposed to just behavioral? Now, when you're looking at the requirements and the specifications, pretty much every line in a good requirements document or a good specifications document should give you ideas for more things to test, right? Everything in there is going to be telling you something about what the behavior is supposed to be, and everything that says it should be like this should, as a tester, jump out at you and say, I should test if it does that, and I should be thinking of ways to do that. And whether they're functional tests or non-functional tests, again, nearly everything in a requirements document or a specifications document should give us ideas for more things that we can test. Now, it can be pretty challenging to set up and check tests for some of the non-functional things. It can be a little bit more demanding to try and create conditions to properly test those. But we'll look for some ideas. So, quick simple example. Again, this is really tiny example, but it gives you the idea. If we've got a time calculation program where the user is supposed to type in a time using a 24-hour clock format, so we give the format for how the user is supposed to type it in, and then it's supposed to give the time in seconds after 00. So basically, they give us a time of day, and we tell them how many seconds after midnight that is. So if they give us a time of 01:59, then hours and minutes here. Come back this. I don't think that's correct. This is actually going through and problems with slides as usual. So if we've got 1 hour and 59 minutes after midnight, then this is actually going through and saying, okay, well, that's 119 minutes after midnight. So this is computing minutes after midnight, not seconds after midnight. Okay. In any case, when I'm looking at a specification like this, I should be thinking of all sorts of different ways to test it. And the idea is that if the input is in any way invalid, then the output should simply be error. So I'm looking at this saying, okay, I'm going to check to see if any, or if conceivably every input in that valid range comes up, it gives me a correct computation, and I'm looking for invalid input and to see if it produces error as output. So you're going to think of all the different edge cases, right? You're going to be looking at 0, 0, and 23 as the boundaries for the hours, and 0, 0, and 59 as the hours, as the boundaries for the minutes. So you're looking at all of the stuff that's just inside that. So zeros for both, 0 and 59, 23 and 0, 23 and 59, right? You're looking at the combinations that are just barely valid. And you're probably also looking at a smattering of test cases in between. Right, looking at a couple of things in the 10s and a couple of things in the 20s and a couple of things in the 10s, 20s, 30s, 40s, 50s, etc. for the minutes, right? Just to make sure that the behavior is correct internally. If you want to get really careful, if you're worried that the developer might be doing something weird, like having some giant switch statement where it says, if the hour is 0, else if the hour is 1, else if the hour is 2, else if the hour is 3, then you might actually consider going through and having at least one test in there someplace that has a check for each of the individual hours, and at least one test in there someplace that has a test for each of the individual minutes. And you're probably not going to go through and do a test for every possible combination, but at least having that, whatever we're talking about, 84 tests for making sure each of those things gets tried at least once. You can consider that as a possibility. And then you're thinking about all the different things that could go wrong, right? So you're looking at things that are just outside of all those ranges. So you're looking at 24 for the hours. You're looking at 60 for the minutes. Maybe trying some negative numbers in there to see if it works for those. You're looking at cases where they give an incorrect format in the sense of they throw a character in one of those spots, any one of the 5 positions, or they have extra characters before or after or in the middle. Right? So you're thinking about what could go wrong in the input and making sure that in each of those cases it generates error as the output. Cases where it's complete rubbish that they type in. What if the user types in spaces? So you're thinking of the different likely errors that you're going to have to deal with and making sure that you test for those. Now, when we're going through and doing this, it's likely going to be the case that we come up with some test cases now, and then we think of some more this afternoon, and we think of some more tomorrow, and we think of some more next week. And so you want to be able to document the test cases that you have. For each of them, you should be going through and saying, okay, well, I've created this test case. This is meant to test blah. So you've got a description of what it's for. You've got a name for it. You've got the actual data, the input data. And you've got something that tells you what you're expecting to see as output. Right? So when we're documenting all this, we're usually going to create a plan someplace, a folder someplace, a form someplace that says, here's all the information about all of our test cases. And that way, if I want to see if I'm testing for something, I can look through my set of test cases and see if I've already got it covered. Or again, if there's multiple people involved in doing this, we can look through and see, has anybody put in a test for this? Right, so you've got this documentation on the test cases you've got. So that's likely to include, again, things like a name for the test. Why is it there? What's its purpose? How did it actually run that test? We'll get into discussions of that soon. But you might have a fairly standard process for running all of your different test cases, in which case you're going to have a little note somewhere saying, okay, to run test cases for this particular program, you do blah. The actual test data, right? Where is the test data for this case stored, or how is it generated, or how is it input? What are you expecting as the results? Maybe even a note on, if you get something else, what does that probably mean? Right, so you're trying to put together documentation on all of your test cases along these lines. And then where that's going to lead us is into the idea of test automation, where we come up with a tool or a script or a program that can take all of those test cases and run them against the program for us and generate some kind of summary of the results. And the idea is that every time we change part of our program, we should rerun all of our tests just in case we broke something. Either we broke the part we were working on or we accidentally broke something else. So this is a lot easier to do if you've got a lot of tests to run if you have some form of automation. Right? Doing it manually is error prone. I can easily mistype something or misread something that comes up. Right? It's highly likely that if I'm doing lots of testing, aside from the fact that it's going to take me forever to run all these tests manually, there's a good chance I'm going to mess it up and say it's broken when it isn't, or say it's okay when it isn't. So we want some kind of automated process for it. And there are lots of different tools out there in different languages and on different systems to try and automate that testing process. So where we're going to be going pretty darn soon is looking at writing some bash scripts of our own to test our code. So for things like the project code. A couple of other things that we can get into are ideas like stress testing, where we say, let's take it beyond just what the program is supposed to do. What if we see what it's capable of? So if I have a non-functional specification that says something like the program should be able to handle, test sets of up to 10,000 items, well, I'm surely going to test it with 10,000 items to make sure that works. But maybe I try it with 20,000 and see if it works there too. 40,000, 80,000, 100,000, 200,000. I start testing it with bigger and bigger cases to see where it is that it finally starts to break down, where it starts getting too slow or starts malfunctioning. And that gives us an idea of what the real limits are. And in a sense, we're giving the client more than what they asked for. Right? We're saying, okay, you asked for something that could handle this. Well, wow, be impressed. We can actually get it to do up to here. So it gives them some growth room in the future. And when we're doing this, when we're stress testing it, if we watch what happens when we hit those limits, if we watch, what happens to the program, does it start throwing out weird values? Does it start slowing down? Does it start doing, what does it do? What kind of an error do we get when we start pushing the boundaries? If we've got that information, then, 6 months or a year or 2 years from now, when the user's doing something with it and they suddenly call us and say, whoa, the program's doing this really weird thing where blah. This kind of thing might tell us, oh, well, actually, that probably means that it's hitting the limit of, and whatever it might be. You've got some idea of what might be causing the problem. So this kind of information can be really useful. A couple of other things that we might take a look at, things like back-to-back testing. Quite often when you're developing a system, it's a replacement for a previous version or an old alternative. Right? We're coming up with something new and better to do what the old one did. So one of the things you can do is to do some comparative testing. Right? Just throw the same set of data at the old system and the new system, and if they both come up with the same result, then we can be pretty sure that, well, we can trust the new one at least as much as we trusted the old one. Right, so this is one way, and it's kind of helpful in convincing the client that the new system works as well. If it gives them the chance to look at, see it does come up with the same idea as your old system, you can trust that it does work. There are some disadvantages with that. It does mean that we'd have to have them both up and operational at the same time, which for some software might not be a big deal, but for big complex systems that are controlling big parts of their operation, that might be kind of challenging. So it is a possibility, something to think about when the opportunity presents itself. All right, we've talked about a lot of stuff with testing and test planning and test documentation and test automation. Clearly, if we're going to do this on a big project, we need a structured approach for it. So having a plan for how you're going to manage testing of your product right from the beginning is important, right? It's just as important as coming up with decent requirements and specifications, and you are going to wind up seeing lots of documentation on test planning and test management and test operation. So when you're looking at a test plan, again, it's going to go through and say, when you're going to take care of different steps of the testing, right? When you're going to design the tests, when you're going to develop the infrastructure, when you're going to develop the scripts to do it, when you're going to come up with the test data that you're going to use, how you're going to run the tests, how you're going to analyze the results, how you're going to document that, how you're going to record that later so that you can go back and say, well, it's failing this test now, but it passed it, up until February 13th or something. So all sorts of things that you want to try and get documented. And a good test plan will go through and tell you who's responsible for all the different steps, who's going to develop and run and monitor all the different tests, who's going to take care of all of the supporting technology and scripts and tools that you need, what the processes will be, where to find all of the test data and all the test scripts. All of that kind of information is going to be documented somewhere. All right. I think that was everything I wanted to say about testing from a theoretical standpoint for the moment, and we'll pick it up with some more applied material next time around. Okay, folks,